the screen for the presentation. Okay, and this presentation is, okay, this is the one.
So yeah, I have my presentation.
Sure, I will actually, first I will present the overall CES presentation and introduce you, Ted,
Okay.
and then you will start your presentation.
Okay, sounds
Okay.
good. Yeah.
Okay, let me start with the first one. Okay. So welcome all to our May 27th Consumer Electronics Society monthly meeting. And we will go through it and then Ted Marina will take over. Okay. So in today's meeting, you're welcome to post pictures and leave your comments, concerns, whatever you want to do in real time via Twitter, as is it indicated here. And here are the names of the officers of currently 2020. I am the chair here, and as you see here, Pat is also on the call. Olga is the co-chair, and she actually put everything together. And here are other people, TK and Avid and Krishna, Joseph and Krishnan and Eric, and we have some other people who are volunteers and they do a great job. And next is we are actually that time of the year when the officer nomination, we like to, we'll be sending e-notice to all members, and Joseph Way will be sending the e-notice to all the members for the chair, vice chair, and secretary and treasurer nomination. And you can nominate yourself or you can nominate someone, and please send their contact to Joseph Way. Okay. And we also, in this year, we are looking for other volunteers because of the other things that we want to do, including speakers and other kind of thing. Please send email to me, or you are welcome to send it to me and Olga both. The next CE Society meeting is on June 25th, and it will be on medical wearable device, the non-invasive continuous glucose monitoring, and also medical IoT area, Internet of Things. We will be discussing that. And here is how many are IEEE members on this attendance? Okay, it's very difficult to see on this kind of things, but anyway, how many are IEEE C members? We actually have more C members this year compared to like 2019, 2020, we have more C members. So this is the process to become a C member. You can go through IEEE or you can directly be a member of the C Society. So these are the two ways you can do. So you are becoming IEEE membership, you can add a C Society membership, or you can be a IEEE C affiliate member. And this is $75 plus $20 per year with basic IEEE and full C benefits. And we have the member recruiting awards. And the benefits of being a C member is that you get 13 magazines for Consumer Electronic Association. And if you have any suggestion for 2020 speakers and topics, please send it to me. Job opportunities, if anybody is hiring on here, please also send your information to me and Olga. I think I cannot see who are the people saying it. Normally in a meeting, we kind of have hands going up and do that. And the job seekers also, if you want, please send an email to Olga and me if you have the jobs and other kind of things available. Jobs, you want some jobs and be specific and send it out. Today's speaker is Ted Marina. Ted Marina is a senior director of RISC-V ecosystem and machine learning business development at Western Digital. Ted is responsible for evangelizing RISC-V, accelerating the build out of RISC-V ecosystem, and marketing the machine learning solution. Ted is the marketing chair for RISC-V Foundation and is also the managing director for open source hardware development organization, the CHIPS Alliance. Okay, and the subject of today's discussion agenda is what is RISC-V and what it is not, the RISC-V Foundation, and the letters to RISC-V statistics and momentum. And he will talk about example of consumer application. And I think I will leave the whole introduction of RISC-V, whether it's open standard instruction set, to Ted. And here goes Ted. I'll stop the share. Thank you.
Okay.
Ted, go ahead.
Thanks. All right. Thanks, Dev. Hello, everybody. Let me get my screen share. Okay. This one. Okay, you guys should be able to see this. I'm going to put this in presentation mode, so it'll be a little bit bigger. Hopefully this will work and it won't swap the screen. Okay, good. So yeah, really pleased to give everybody an overview. As Dev had said, I have a few different responsibilities for Western Digital. Primary one is the RISC-V ecosystem. I also do some things with machine learning from a marketing and business development point of view, and getting involved in zone storage now. So kind of a trick of a few different trades, if you will. I've been the marketing chair for the RISC-V Foundation since the end of 2016, early 2017. So I've actually been involved in RISC-V for over 3 years, and I'm really excited to share with you sort of where we're at and what's happening, where we're going. So the way this presentation is arranged, and I believe we have about an hour, so I think this deck will take a little less than that, but if there's a lot of questions, we might complete the hour. But the first about a third of the presentation, I'm going to go through RISC-V, the RISC-V International, the organization, kind of, try to sort of explain to you why it's popular, why it's taking off. And then in the last 60% or so of the deck, I tried to put together all the different consumer-oriented applications where RISC-V is being used. And one of the challenges is many companies aren't necessarily going to open the kimono, right? So there's a lot of things that are in development, but of course I can only share what and put into the market. Okay, so let's get it. And I'll try to keep an eye. I don't know if there's going to be someone sort of monitoring the Q&A or chat window, but Dev or Olga, whatever, if you guys want to stop me, that's fine. Okay. So RISC-V is not an architecture. It's an open instruction set architecture. And so basically it sets the specification for the architecture. It doesn't say this is how you have to implement it. It just says these are the instructions. I don't know why that is on a timer, and I really apologize, but I'm going to move on from this slide shortly. It was actually started in Berkeley in 2010. We actually just had our 10-year birthday, if you will. The best specification was actually frozen, the base specification, and I'll explain that in a second. And really today we have over 200 companies. So just a tremendous amount of growth as we've been moving forward. And I think there's a couple of reasons that I want to explain sort of why from a big picture point of view over the next couple of slides. So one is the fact that if you think about processors and you think about the architecture, they're basically the von Neumann implementation, and the architecture choices that we've had, even some of the RISC architectures that are around are really decades old. And when you think of the pace of electronics and the pace of innovation, it's kind of remarkable that, you know, these implementations have actually been able to continue to be relevant. So there is sort of you know, a benefit as these implementations are kind of known, if you will, and there's an infrastructure from a tools and software point of view, but there's also baggage. And that's, I think, one of the benefits is that RISC-V really unlocks innovation because it's an open architecture, right? It allows the end user to optimize, to pick and choose exactly what's needed. So those are some of the key points. And if you take a look at sort of how things have evolved, you know, in the 80s, there was, you know, dozens of companies, a lot of them making their own specialized architectures and complex instruction set architectures. Obviously, Intel started to become dominant, and in the 90s, you sort of had a bit of a consolidation, you know, where the desktop and server were, you know, Intel was driving, and ARM started to become popular in embedded. And of course, there's PowerPC and a few other architectures in there. As you moved into the 2000s, you know, there started to be some innovation because of mobile, which was really helping drive that. And you started to see a few of these open architectures, Open RISC, Open Spark. I think the idea was, and RISC-V, I think, benefits from the fact of how powerful Linux has become from the software side. So everybody has seen the value. Everybody's sort of very comfortable and familiar with the idea of collaboration from the software side. And RISC-V is really the first organization that's been able to capitalize on that energy, the collaboration. And I think the, you know, the benefit is because, you know, it's not tied to a company. It's not an architecture that you just have to adopt. It's a specification. So, you know, it allows you to really, truly innovate. And one of the things that I like to say is that it basically hands a microarchitecture license to you at no cost. So at a top level, when I talk about RISC-V, and people will ask me, you know, what are the reasons, right? And some of the reasons are highlighted in this sort of bubble chart here, but I'll just explain a couple. So when we, sorry about that. When we say modular, I'm trying to get my mouse over here. When we say modular, what we mean by that is the specification says you have to execute the base instructions, but there's a bunch of extensions that are optional. So the minimum, I have no idea why that auto moves, and I apologize. The minimum, the specification is the base spec, and then you have extensions that you can use. The other thing that I think a lot of people like is the stability. So the fact that RISC-V, it's a fixed ISA. So, you know, if you have code that runs on RISC-V, it's going to run for really another key point. You know, one of the things that's also really exciting about RISC-V, and I've really got very energized when I went to my first conference in July of 2016, it was just the collaboration, it was just the energy about all these different stakeholders that wanted to participate. And, you know, whether it was people who were IC chip designers, or it was, you know, IO, memory, or, you know, foundries, or people on the software, the development tool side. And of course, you know, the university and the research side has also been, you know, very instrumental in moving things forward. And so I think, you know, the fact that we have this, you know, really energetic ecosystem is really providing a significant energy that has allowed the organization to really not only reach critical mass, but, you know, accelerate even beyond that. Again, if there's questions or whatnot, just, you know, raise a hand or ask me. I don't know if people are allowed to interrupt, but that's fine with me. So I think people recognize today that the amount and area and the processing requirements are, you know, basically more and more diverse. So, you know, we obviously have seen an explosion in data center cloud applications, Mobile, continues to grow and also expand its reach. IoT devices, have their own challenges in terms of lower power and connectivity, and automotive, industrial, and so on. So there's kind of a continual growth here of the requirements for processing. And let me just take a quick look because I see this little window up here, the chat box. Okay, yeah, okay. So if my audio keeps cutting out, I'm going to cut my camera just to help. Hopefully it will not any longer.
Ted, do this now. It usually helps. Because
Okay.
the more people add, the higher traffic will be. So do cut off the video on yourself.
Okay, just a second here. Let me do that. Okay. All right. So the interesting thing is, where and how companies are leveraging it. So just to give you some example of some various applications in embedded, Microchip announced their PolarFire SoC FPGA, and this uses a hardened RISC-V subsystem. On the next slide, I'm just going to go to it and then I'll come right back. Because I want to point out sort of one of the things that RISC-V made possible that was not possible with other architectures. So the PolarFire architecture, there's an FPGA down here. In the blue boxes, this is all hardened logic, and this is a quad 64-bit RISC-V complex. So this is an applications class processor that was incorporated. This IP was from Sci-5. And what's really interesting about this architecture is Microchip had identified that certain applications, it was really important for latency, for interrupt to be very structured. In other words, the processor needed to be able to respond in a fixed amount of time. And so, it couldn't have something where there was an interrupt and then it caused the processor to take a significant more amount of time to go and respond. So this like real time requirement in many of the applications was really critical, but they also needed to run Linux. So, you had this kind of dichotomy here where we need multiple apps processors, but we need real time as well. And so what RISC-V allowed them to do was to be able to have the option to throw a switch, if you will. If you're running a real-time application, you can turn off certain branch prediction functions, which basically eliminates the variability. And so if you look at an A-class architecture, what the interrupt service routine variability will be in terms of cycles, you can see it's a pretty wide-ranging distribution. It's literally flatlined. So that's obviously very compelling for those applications, and that's something that really was not possible with the other architectures unless you have an architecture license, which is extremely expensive and is really only available to a small handful of ginormous companies. So this is one of the interesting benefits of RISC-V for that application. There's a lot of things happening with AI and machine learning with RISC-V. So many different companies are implementing architectures along those lines. The high performance compute, the European Processor Initiative, has also selected RISC-V. Later in the presentation, I actually have a couple slides from Greenwaves. They make a very, very low power parallel processing architecture based on multiple RISC-V cores for like battery powered applications. It's a very, again, unique and innovative implementation of RISC-V. And there's other examples as well. The wearables application, I got just a couple slides. I don't have a lot of details on on the Amazfit smartwatch, but I wanted to just, sort of highlight the info that I did have. And actually at our most recent RISC-V summit, which was a conference held in December of last year, Samsung had actually talked about how they're using RISC-V in embedded controllers. And I'll kind of highlight, the path that companies take as they get into RISC-V. Okay, so some of the other areas that I also like to highlight where there's some significant innovation happening are in a few different application areas. So sort of highlighted here, because RISC-V is ground up, we have a lot of interest in security. There's a lot of companies doing a lot of things with security. The one that's interesting to highlight is Google. Google has a program called Open Titan. So they previously had a root of trust device called Titan, and now they're working with a consortium of companies to develop Open Titan. Western Digital is one of those organizations. And so the benefit for those of you who are familiar, when you have security applications, the more transparent you can be, the more pairs of eyes that you can put on your solution, it's going to be reviewed, it's going to be scrutinized at a much higher level. And the security, with that tends to be much, much higher. So we see a lot of activities and energy around security type of applications. There's others here too. I don't want to go through it all, but I just wanted to sort of share with you some of the other areas. So being part of the marketing group for RISC-V, we worked with a few analysts, and one of those analysts, Semico Research, had done an extensive survey that they released at the end of last year. This analyst report showed the number of cores that they believe that RISC-V would ship by 2025 to be over 60 billion. So, if you think about I mentioned earlier, how do people get started? And I'll show you sort of an example on this. Most companies will start with replacing whatever core they're using to control the larger SoC. When you think about chips today, there's usually, multiple processors that could be running an OS. It could be handling, some various tasks. But you also have a tremendous number of these small embedded cores that do things like power up reset, and it manages, trims voltages. They do all kinds of like sequencing functions and waveform, generation, and so on and so forth, right? All these control aspects that are needed in an SoC. And that's how companies tend to get started. So what you find is many companies today are already shipping devices that have RISC-V cores, and many of these architectures have multiple RISC-V cores. They're all, these little embedded cores. Companies started and tend to, take additional steps, and continue to utilize the fact that the ecosystem for RISC-V is continuing to grow. But the bottom line here is you can see across several markets, there's pretty widespread adoption, with industrial sector being the largest. And I think the reason that the industrial market is pretty excited about that is because of the stability. They can count on the fact that the instruction set is frozen. So they know if they write software, which they usually have really long life cycles, that it will stick around and it'll still work in the future. So, RISCV International is the nonprofit organization. I'm the marketing chair for that group, and we're all about promoting the specification and basically making sure that the different groups that are part of the organization continue to accelerate standards and drive further adoption. This is just a who's who of all the companies that are currently in the foundation. This slide is a couple months old, so it's already out of date. Today we have over 200 companies. To kind of give you an idea, probably the next slide's a little better. this is kind of a growth chart here. So where we're at today, we have 200 companies and organizations and 350 developers and advocates. And these could be, consultants, but it also could be, nonprofit groups. And so, the growth that we've seen is just tremendous. I got involved, as I mentioned, down here in late 2016. And, we've continued to accelerate and grow the membership of the organization. The organization today, we have a lot of technical groups that are working on various standards, and they're in a variety of areas. I think this is another key benefit of joining the foundation, is if you want to set and steer the course for a particular, whether it's a software tool or a particular extension or what have you, you can be part of the group and steer and influence and collaborate. So for example, the V extension this is for vectors. This is a really active group because a lot of people are looking to push this to standardization for machine learning, and vector extensions are extremely important for CNNs and so on. But you see there's a lot of different groups here, from debug, different extensions like bit manipulation and so on. So lots of different groups where we have a lot of different activity moving forward. In terms of software tools, if you weren't familiar, we have a bunch of different versions of Linux that are now supported. Many more 32-bit RTOSes, so free RTOS, which is the Amazon web service supported. OS is popular, Zephyr, and so on. A number of OSs are available that people are using, and it's a bunch of commercial software as well. So there's actually quite a bit of broad support, and this is certainly making it easier for organizations to move to the technology, because if they previously had something on an OS, it's much easier to move to this as a processing standard. Let me see, got a question here. How does RISC-V prevent against covert channel attacks? So, the architecture itself is, just the spec, right? So it's just the instructions that you are required to implement. But what's interesting is, because the microarchitecture is under your control, you can implement things to prevent whatever attacks or whatever security issues that you're most concerned about. So, if you want to put in, DPA resistance, to your design, you can do that. There is a number of companies. There's a company called Dover Microsystem, which has a really innovative way to actually, on an instruction by instruction basis, make sure that, the core is operating as it should. Hive is another security company that, has this implementation where they containerize the software. So there's the software that's totally secure, and then there's the one that you'd have more for access and update and whatnot. So like a trust zone, if you will. So there's a lot of different implementations, and the fact that you have that open nature allows you to, as I mentioned, implement a lot of different security solutions. I'm not like a security expert, but hopefully that gave you enough of an idea. So there's a lot of ways that you can engage with RISC-V. We have a lot of different events and so on. I guess I just want to highlight the summit that we have. So every year in December, we have our major conference. We are planning to have it in person this year in San Jose at the San Jose Convention Center, knock on wood. The event last year, we had over 1,600 attendees. We had more than 40 sponsors. The expo floor was, really engaging, lots of technical talks. I think that's really the key, is people are always, basically presenting with a mixture of research, companies, universities, what have you, these various technical papers on a lot of different topics. And so actually our call for presentation is now open. So I just took a snippet here, but there's ecosystem talks, hardware, SoC, cores, security and functional safety. Oh, sorry, I just moved the mouse the wrong way. Come on. Security and functional safety, as well as tools, system architecture, and debug. If you want to get involved or see some events online, you can go to the meetup page that's here in the lower corner. And that's the Bay Area meetup group. Normally we meet in person, but over the last couple of months, we've just been meeting online. So we actually, I know, have another event coming up next week or the week after. So you can kind of get involved. Now the one thing I just want to plug CHIPS Alliance. So I mentioned that RISC-V just sets the specification. One of the organizations that's just a year old now is CHIPS Alliance. And this basically was founded by Google, Western Digital, Sci-Fi, and Esperanto a year ago. But now we have about 20 companies. And this is really to like take where the specification ends and implement RTL and also do open source development tool work. So this group has the following, is just kind of a quick member snapshot. Also recently had Samsung join. We have a number of work groups that work on everything from like interfaces such as AIB, which is a chiplet interface. You can use it for anything, but they're part of the group. We have a cache coherent memory fabric called OmniExtend, which is actually based on a tile link, which is a RISC-V coherent bus. Swerve is a Western Digital RISC-V implementation that was brought into the group. And then there's also these open source tools that are part of the organization, like Verilator, which is a very popular simulator. There's a lot of work being done on tools as well as various hardware. So if you want to know more, there's actually a annual report which we just published, chipsalliance.org/chipsalliance 2020 annual report, which gives you like a quick summary of what's happened in the last 12 months as the organization's ramped up. Okay, so I want to go and explain, and then we're going to shift into applications next. But I want to sort of give you a case study of how companies tend to get going with RISC-V. And this is actually documentation from Nvidia. So in late 2016, they had, or 2017, they had done a presentation at a RISC-V workshop. And they basically had said that, they have this internal core called Falcon, and the company really needed more performance. And so they were going to do like the next generation Falcon, but they said, hey, let's evaluate all these different architectures. Sorry about that. I don't know why my mouse is so sensitive. And so they basically, done this analysis. They basically wanted something that was 64-bit, but it was embedded. They needed a certain amount of performance, and they wanted like tightly coupled memory, security, and so on. And what was interesting is, you can see that, so this RISC-V Rocket is a particular type of RISC-V implementation. Doesn't have tightly coupled memory or this functional simulation model, but NVIDIA basically saw all the other yeses, and they basically figured, oh, well, we can make an architecture ourselves with tightly coupled memory, and worked with the organization to create a functional simulation model. And so that's why they ended up going with RISC-V. So they have their implementation is called NV-RISC-V. It's a 64-bit implementation. So it's an embedded core. And what was interesting is they had this snapshot here where they showed that, the first time they had used this, this is a couple generations ago, they put the RISC-V core next to the Falcon core. Just to allow for software, translate or transition. And, what's for them, what was a real benefit is, they were able to implement and get everything that they really needed, because again, the instruction set is open and they were able to do the full up implementation. So now, they ship SoCs with many of these NV RISC-V cores in them. So, that tends to be kind of how people get started. Let's shift gears now, and I'm going to start to show you some different examples. And, again, depending upon, what amount of information I have for you, some of these will be a little higher level, others, these will be a little bit more detail. So Google actually had presented at a workshop in 2017, or no, 2018, actually. They have a image processing unit, the IPU, and it's basically interfaces to the image sensor, does the processing, and it basically is a controller that's dedicated to do various processing. So, you're not wasting the power of the full-on core. And this is something that was integrated since the Pixel 2 device. And again, this is a RISC-V based architecture, and they have multiples of these in the device. And the benefit that they had derived was that they can do HDR much faster at much lower power than having the application processor do it. So this is, I think, a really interesting example of how they were able to move forward, leverage the open architecture, and really get a bang for the buck, if you will, benefit, lower power, more performance. The next application, so AMD's Technology is a leading IP company, and they are absolutely one of the top 2 RISC-V IP organizations. And they focus on a lot of IoT applications. They sent me a few slides here that I wanted to highlight, because I think this is really interesting, because this is definitely a hot area in consumer, is wireless stereo, so earbuds and the like. So there's obviously a lot of different interfaces and various challenges that are required here. And what Andy's really takes advantage of, and I'll kind of build this out here, is you see this ace with the checkbox. Whoops. They're very, they take advantage of the fact that you can add custom instructions, custom extensions to RISC-V. And so Andy's not only provides the IP from the hardware side, but they also provide the tools, so you can implement all the software for the core that's implemented. So they have custom instructions that allow you to implement the noise cancellation, the various codec formats, and so on. So again, I want to show you one of the implementations here. So, for example, the active noise cancellation, there's a certain amount of sample time that you have, and you have a certain frequency of the processor. So, you have to do these functions in so many clock cycles. So there's obviously design limitation in terms of time and obviously power. And so the way that they tackle this is they're basically saying, okay, you can do it in hardware, and have the parallelization, but obviously when you do that, you have this pretty fixed algorithm. So you have that implementation, or you have something where there's lots of flexibility, but because of the larger size, you're you have a power consumption. And so sort of what they have come to realize is something sort of in between here, provides the best of both. And So they've actually implemented a architecture. So this, let me just move it forward so you can see. Yeah, so they have this D25F is one of their RISC-V architectures, and they have these various custom instructions that do things like the background fur and so on. And so those extensions are really customized for this wireless stereo type of application. And the result, and again, the fact that they're able to take advantage of RISC-V is that, there's a performance speed up here at a slower clock frequency. So, much faster performance with their custom instructions for fur. I can't remember what that algorithm does, but the whole a noise control algorithm is significantly sped up. So the RISC-V core plus the custom instructions at 80 megahertz. So you can see there's quite a bit of benefit to the that type of implementation. So, this just sort of highlights that, yes, there are end companies that obviously are large with a lot of resources that are doing it, but you're also starting to see IP companies now, get to this level of assistance to help end companies with their implementations. I'm just going to kind of keep rolling here. So this next example is RISC-V, which Xiaomi is a company that owns Huami, and which is the silicon arm of the organization. And so you may have seen their line of Android OS watches, or Wear OS is now called. So these are actually based on RISC-V. The organization was able to get a better standby, a longer standby time, and they also were able to, the way they were able to do this is by implementing some AI functionality. So the watch didn't constantly have to, connect to the smartphone or, to the cloud to do that level of processing. So they actually implemented 4 cores, one for cardiac biometrics, ECG, and heart rhythm abnormality. So again, really specialized implementation. This is actually based on a Sci-Fi embedded core. So that E301 is a Sci-Fi implementation. And obviously they took that and had done additional customization. They had analyzed, much lower power consumption than some proprietary silicon implementations. And so this just kind of, again, gives you a window into where the RISC-V is being used, even though it's not like, labeled all over the chip. This implementation allows them to have a really compelling story in terms of battery power and device life. So I'm going to shift gears a little and talk about motor control here. So, you might think, hey, motor control, that's only for industrial applications. And obviously, it is. There's motors, and there's also areas where you have motors and motion control. And Trinamic is a company out of Germany. They were actually recently acquired by Maxim Integrated. So, Maxim has a lot of analog expertise, and Trinamic does a lot of the mixed signal implementations. And so they had recognized that there'd be a real benefit to be able to combine the motor control and hardware with the right processor. So they were firm believers in the hardware implementation for the control algorithm. Don't put it in software because of, again, interrupt latency issues and others. So they had an implementation that looks like this. Their device is called Rockinante. I can't remember exactly how to pronounce it. But you can see this is a full up implementation here. There's a lot of mixed signal analog functionality. some of the common peripheral set that you'd find, power and such. They really looked at RISC-V and loved the fact that, you know, the extensions were selectable. There was another interesting aspect from them is the fact that they looked at RISC-V and said, hey, we can pick an architecture and then choose the IP provider. And it really turns the decision process upside down for a system architect. Normally, you would interview a vendor, right? So, hey, I'm going to use this particular architecture. You already are tied to that vendor. And, you know, with RISC-V, what's really exciting is that you can pick that as an architecture, but you can, you know, you still have flexibility to choose your IP vendor. And there are a large number of vendors of IP for RISC-V, and I think Trinamic really appreciated the fact that that was another benefit for RISC-V, which I hadn't previously mentioned, so I just wanted to throw it out there. This is actually a physical layout that they shared on a recent presentation. So, you know, the core only takes about just under 10%, given the customized implementation that they have. You know, you can see the analog and peripherals are obviously a big majority of the implementation. So this is just, again, another area of implementation that they had utilized. I'm going to shift gears and talk about, this is a subset of a presentation that I and one of the CTO organization leads also talk about for Western Digital. So, you know, when we were looking to implement RISC-V for our controllers, our flash controllers, you know, there were a few different challenges we had. Things like the number of instructions per clock cycle. That was definitely something we struggled with. Poor branch prediction rates and a low instruction cache hits. And so, you know, there were a lot of different architectures that we had looked at, and obviously we've been using various ones. And, you know, as we implemented our own implementations, you know, we were able to get, you know, quite a bit of performance. So there was like a 2x improvement in the number of instructions per clock cycle, much better on branch prediction, and also improvements in terms of cache hit. So, you know, again, the fact that you have the ability to utilize this microarchitecture, you know, it's a significant, can be a significant benefit. You know, but on top of that, we started to, after we introduced our first core in early 2019, we had other requirements, and some of those were multiple processors. So, you know, there's multiple processors used in some of these designs, and, you know, the demand went out for a multi-threaded architecture, because these processors do an IO call and then they're just sitting there waiting. So one's doing an IO call, it's sitting waiting. Another one does an IO call, it sits and waits. And so if there was a multi-threaded embedded core, it could potentially replace two architectures. There was also a need for a very small core, but with good performance, to implement sequence logic, replace state machines and other fixed logic. And so those were some things that were a new course. And I'll show you just a summary chart on the next slide. But the organization, Western Digital, was able to introduce the world's first dual-threaded embedded core. You know, again, that was made possible with the openness of RISC-V. And the group has also really seen a time to market advantage with these architectures as well. So, you know, it doesn't mean that it's all roses. There's definitely a ramp up time and a learning curve and so on. And every company has to go through that. But these are some of the benefits at the end of the day. And this is the current roadmap. So all three of these cores, the Swerve core EH1 was the first core introduced at the end of 18, beginning of 19. And then the EH2 is the dual threaded. The EL2 is the small performance core. So all three of these are in the CHIPS Alliance GitHub. So any individual or any company that's interested in potentially collaborating, wanting to use these cores, there's development in an open collaborative environment that's being done. We've actually partnered with Codasip. If companies want commercial support, Codasip is an IP company that has a support package for each of these cores. So it's super exciting that Western Digital has been able to use them themselves, and we're also donating it to the open source to continue to accelerate RISC-V adoption. So it's definitely one of those feel-good stories. And it's a win-win. This is just a quick block diagram of the EH2. So it's a superscalar architecture, and it has two sets of registers, basically two sets of control that allow a certain amount of up to two instructions per clock cycle. Again, it just depends on what you're running for the software functionality. The core marks, the EH1 core is about 4.9 on the core marks, and with 2 threads, it runs about 6.3. So it's quite a good performance. And the implementation, it's a 32-bit core. It implements integer, multiply, divide, atomic instructions, compressed instructions, and these bit manipulation extensions. We have publicly shown sort of the areas where the swerve cores will be implemented in products down the road. So this is something that is being done, and we have some other areas that we're also looking to put some of the smaller, newer cores. So again, this is just another area of highlighting where we're using the technology and where it can fit. Then this is the last example that I want to show, is just talks about this company Greenwaves. It's a small organization headquartered out of France. They have a few different locations. They have a multi-core architecture, RISC-V based. It's really targeted for very much at the edge, at the very edge. So battery applications, whether you need to put this in an object, they have like people counting applications, and they have many of these other applications that are potential targets for this. Let me just move this forward. So they have the GAP8 was the first processor that they introduced, and this was a up to 8-core RISC-V implementation. The architecture itself, it allows, for various levels of power consumption as well as processing capability. And then they have recently introduced the GAP9, which is enhanced architecture. The real benefit here is it's like MCU class consumption of power, but much higher performance. I wouldn't say application class, but much higher performance. And there's ability here to kind of scale and make the transitions from deep sleep to signal acquisition to analysis, if you will, and even doing inference and other types of applications. It's not just limited to inference. So the implementation that they've put together here is really leveraging the RISC-V architectures in a parallel manner. So it's quite a unique, innovative approach. So these are those are the application examples that I wanted to go over and share with everybody. And let me just sort of summarize here. Again, I think some of the benefits and what people have seen is that the architecture, you can pick that first and then choose where you want to get the IP. It just gives you that level of control and flexibility. And if the vendor doesn't work out, you don't have to throw your software away when you do your next design. You can simply go to another IP vendor, and that software, as long as you implement the same extensions, obviously the base has to be implemented, but if you implement the same extensions, then you will have software preserved. So all that investment moves forward. Again, you can implement exactly what you need. So if you don't need certain extensions, you don't have to implement them. If you want them, you can. If you want to add custom instructions, you can do that. So it truly allows full implementation, full optimization. You can customize exactly what you want. So maybe your application is like the Greenwaves, super low power. They've absolutely optimized for that. Or if you want to optimize for performance, or and or cost, right? So all these levers are available to you and much more under your control than with other architectures. And I think the other benefit is that there's an ability to leverage the open source ecosystem. So there's many tool vendors that are supporting the RISC-V implementation. You can find both commercial compilers, you can find open source compilers, you can find commercial operating systems, you can find open source operating systems. There's a number of different implementations from debug and trace and so on and so forth. So there's a lot of different options that are available. Okay, I just noticed a question. Is RISC-V used in 5G products? So early on in the presentation, there was a quote that I had showed about Samsung actually at the RISC-V Summit in December had mentioned that in some of their modems, they're actually using RISC-V as a controller. So, I mean, I don't know if you, so I can't tell you 100% if that's, what you would consider 5G, but that's, that's the only information that I know of and has been publicly shared.
And there is another question: how RISC-V protect against covert channel attacks?
Yeah, I had answered that earlier.
Okay, and there is another question on the YouTube channel, and that one is: can you explain how Western digital interests in RISC-V? I usually see chip companies promoting this.
Yeah, sure. So for Western Digital, I think there was a couple of different benefits for us. So one benefit that is maybe not inherently understood is, in addition to the customization and being able to implement the controller that we want, we also found that when we were working with an IP vendor, we would basically have a core that they would have a core, and we would say, oh, we like this core, but we also want this function. And so that was obviously a function that helped us optimize something, whether it was for better flash performance or longevity, endurance, whatever. And we would pay the IP vendor to do it. That was okay. That wasn't a problem. But the issue was that that IP vendor, like it or not, now has the knowledge that that's valuable to us. So they're able to make a generic version of that IP, and they can sell it to our competitors. So IP leak is one of the reasons one of the other reasons why we like to have RISC-V and have that control in-house. And then the other application, the other overriding reason for us, it's about open standard interfaces. And look at what processor vendors are doing. Because Moore's law has completely run out of steam, you can't just double the cores and double the speed anymore and charge the same money, right? So those architectures, the way that they're trying to grow the business is by locking down interfaces. And so they're putting these proprietary interfaces and basically driving customers to say, well, if you want this particular peripheral, that they have to buy that from me. And we believe that that's really threatening to the business, because we're all about attaching to implementations. So for us, it's about making sure long-term that open standard interfaces continue to exist.
Ted, this is Dev. A quick question about the farmer level, like operating standard operating system compatibility. Suppose the processor that you did with Western Digital multi-threaded operating system, multi-threaded uh, board CPU, and that is excellent. But what about running some kind of a standard like a FreeRTOS or Linux on those kind of things?
Are you talking just in general about RISC-V, or are you talking about the RISC-V architectures that Western Digital has created?
I mean, you can actually do that way, RISC for whatever Western Digital did, as well as, if somebody else does a multi-threaded processor, how do you port a operating system? Because one of the things I see when you do a processor, porting the operating system and other kind of thing is a big challenge, and it takes a lot of expense. So I wanted to hear from you how it is, like suppose I want to port FreeRTOS or Linux, how difficult it is and other kind of thing.
Yeah, so I would not claim to be a software expert, but what I can share with you is there are operating systems, like commercial operating system like ThreadX. A lot of folks in defense and industrial customers use that operating system, and there are companies that have used ThreadX for other architectures. RISC-V supports that, so now they're able to move over. Yes, it takes some effort to do that, but the fact that the OS is there allows you to recompile. FreeRTOS is the same way. There's Zephyr as well. Those are implementations where there exists implementations in FPGAs that people can take their code and target to a board that has a soft RISC-V and an FPGA, or obviously some hardened implementations. So I would have to kind of pull in a software expert to kind of address any next level of questions. But I think all of the main operating systems that folks are interested in are supported. The one thing I can say for Western Digital, we had some internal tools, like we had some firmware tools, and we did have to do work ourselves to obviously move that to the RISC-V implementations. But for us, that was heavy lifting, but that work is now done and we can leverage it.
Thank you, Ted. That's what all I wanted. Yes, thank you.
Okay, another question from Tom Coughlin. What are the barriers to RISC-V use in consumer products?
Oh, hi, Tom. So I think in terms of barriers, so the barriers there, I think, are not really significantly different from a lot of other barriers in terms of whether it's an industrial customer wants to move to it. So probably the biggest barrier, I would say, is a lot of consumer products are based on Android, and Android is not yet supported for RISC-V. So, that would probably, in my estimation, be the biggest barrier. But if the consumer application was running an RTOS, which is already supported, I think the barrier is fairly low. There's definitely a lot of IP companies that can implement RISC-V architectures. There's design service organizations that can actually make SoCs to get you a GDS to tape out. So I think the other barriers are actually not that significant if the operating system is supported.
Another question.
Let me see. I have another question. What is the range of real-time response time in WD applications on RISC-V? I'm not really sure I understand the question. What is the range of real-time in Western Digital applications on RISC-V? I'm not sure if you're talking about
Michael, can you explain it? You need to unmute.
Yeah, Ted, this question. So you have an application and basically interrupt service routine. I should guarantee in a 10 microsecond, 5 microsecond, 1 microsecond, 1 millisecond. Okay, so what is application and is real-time critical application for the storage, or you very flexible and not really depends on real time? There's a question.
Oh, okay. And so I would say that first thing I'm going to say is I'm not 100% sure of the response I'm going to give you, but I'm going to give you my best guesstimate. So I think in general, we want to have the shortest response time that we can for interrupts. It may be negligible in that, you know, when we're dealing with non-volatile storage, you tend to have microseconds, right, to be able to, you know, before you're responding, because it takes time to access the data, and sometimes it's hundreds or thousands of nanoseconds. So I think in general we look to minimize the interrupt service routine response time. I do know in our cores we have a configurable interrupt with priorities and such. But that's the best answer I can give you. If you're really super interested, you know, you can send me an email and I'll get that question answered for you.
Yeah, thank you. Yeah, it's just general question. You mentioned about real time and you have a slide that compare different architecture and RISC-V. So the just question came from the slide.
Sure.
I have a next question. Sorry about that. So do you have a cache partitioning for the multi-threaded systems? I mean, cores that you have.
You mean, well, the devices have an instruction cache, and you can do tightly coupled memory. So what do you mean by cache partitioning?
Okay, so each core, basically you allocate for individual core, individual caches, basically cache ranges. Okay.
Yeah.
Okay, thank you.
Yep, sure. Outside of the RISC-V cores, what tools do I need? There's a few different ways that someone can get started with RISC-V. I think a lot of folks, they tend to utilize an FPGA board in an initial implementation. So you can actually find, you know, for example, Microchip has an implementation where you can go and download to their FPGA board, put a RISC-V core in it, and you can run free RTOS. There's a Zephyr that's also available that runs in a number of cores. There's actually on the RISC-V website, there's a getting started guide. And let me just want to see if I can find that, because I'll put the link in the chat box. But there's actually a getting started guide that actually talks about whether you want to use a RTOS or like a Linux implementation. I'm just trying to see if I can find it. Yeah, I'm just gonna put this in the chat box so you guys can have it. Where's the chat box? Okay, hold on a second. Okay. So this has been, yeah, no, I got a Q&A box. I don't have a chat box. I don't know.
Okay, so yeah, we have something in chat. Oh, it's a Kevin press release. Okay, PolarFire Society, Microchip. Okay, excellent.
Yeah, I don't know why I can't see the chat box. Oh, maybe it's under more. Hold on a second. Oh, there it is. Okay.
Yeah, it's a Kevin Cameron.
Yeah.
Microchip press release page on the PolarFire and TED GitHub RISC-V getting started. Okay. Guys, we're over our time limit, so let's wrap it up.
Okay, thank you very much. I really appreciate it. This is my contact info. Please reach out to me. You can email me or follow me on Twitter or LinkedIn. Thanks a lot. I've had a great time, and hopefully you guys learned something.
Thank you very much.
Thank you, Ted. I appreciate it.
And on that thing, we're closing this session, and we'll see you in June.
Bye-bye.
Bye, everyone.